So for the next one, we will see one of the most advanced simulation tool to emulate or even digital twin of the system with a new paradigm. So I just wonder whether Professor Pedro are you here, or someone from LIS, or yes, Pedro, please go ahead. So you have 15 minutes for the presentation.
Will do. Sorry, I will share my screen now. Just a second. Let me sharing my screen. I'm presenting. I am starting my present. I am not sharing my screen yet. Sorry. Let me share my screen. Second screen. This one. Share. Just a second. Just a second. Let me see if you see my screen now.
Yes, but Pedro.
Okay.
Please go ahead.
So thank you very much for the introduction. I mean, in my presentation, I will introduce, let's say, the system we use for, or the real-time simulation system we use for, let's say, for developing and yes, for developing the control system of the batteries that we had been presenting before. These batteries, as you can see here, I will not get persistent on that, but usually they can offer services to the transmission system, okay, to, flexibility or ancillary services. They allow also enabling new mechanisms and new opportunities for participating in markets, okay, by trading flexibility services, or maybe enabling new players as aggregators to I don't know, to arbitrate energy, and based on that to develop new use cases and new business models. And in addition, as well, these batteries can provide services to the end users, the one connected downstream of the batteries, by providing, I don't know, for example, power quality services. Today, these batteries could be very important from the perspective of providing security of supply in front of, I don't know, failures, attacks, or I don't know, resiliency in case of any kind of unexpected failure, okay? But the matter is, how do we control these batteries once installed, okay? In such a case, as my colleagues presented before, we have used here in this project a 3 layers structure, okay? I mean, this 3 layers structure is a kind of simplified, let's say, adaptation of older models, okay, which are more sophisticated to go covering more zones and areas. But here we have at the bottom level what we call the first, I mean, you can see here in the first layer all the assets which are from the substation, okay, transformers, switches, and so on. And here at the right side you have the batteries, the power converter, transformer, the switchgear. At this level is where the first level controller is installed, okay? It's a kind of controller which is installed here. It's communicating very fast with the power converter, and is modifying its power references for reacting to the variation of the magnitudes at the point of connection of such a power converter, okay? This first level controller will interact with this second level controller, what we call the area level controller, okay? This area level controller, or the substation level controller, is the one receiving signals from its natural environment through its, let's say, area of influence, okay, from PMUs, RTUs, from the power system. And based on that, it will run some algorithms that are focused on improving the performance of the area where the battery is connected, okay? Therefore, this flexibility or ancillary services which are provided by the battery are not responding to kind of remote optimization, but they are responding to real-time references and models which are receiving signals from the SCADA of the TSO and the DSO. And eventually, this second level controller will communicate with the third level controller, which is the one calculating the schedules for the operation of the battery according to given missions profiles, okay? So This third level controller is the one calculating the schedules for participating in markets or for providing given services. Okay. So, well, I will not get into all the details. Okay, there will be a kind of logic, let's say, organization of this. Okay, there in blue, you can see, let's say, some functional blocks which are related to the local control, the one closer to the hardware. Okay, some local SCADAs and first level controllers focus on, as my colleagues mentioned, voltage regulation, frequency regulation, and inertia modulation. The substation level, the green area, we will have the second level controller, which will be running other algorithms that will be focused on improving the performance of the area. And this second level controller will be communicating with the SCADA from the system operator or from other signals, or interfacing with the system operator actually. And in orange, you can see here the third level controller. Okay. So the high level, let's say, calculations. Okay, here is a more, let's say, physical implementation, a more physical description. You can see at the right, the first level controller. In the center, the second level controller, which actually is our concentrator. Okay, all the signals are concentrated in the second level controller. We will receive the signals from the measurements units, RTUs, PMUs from the TSO. At this second level controller, we also receive references and schedules from the third level controller, in this case through the internet. I mean, there will be VPN specific connections. In this case, we are using in this project, a kind of fog computing, okay? I mean, the third level controller is actually a server which is generating references according to local needs, okay? And this third level controller actually is the one communicating with the FEC platform, okay? Is this with the one communicating with the, let's say, with the cloud-oriented solution, okay? For, let's say, for allowing interaction of the different players and connecting with other data spaces which are related to our applications, okay? In addition, on the top center part, you can see how the SCADAs, my colleague presented before, are there, okay, are connected to the second level controller. The point is, how do we develop all this structure? Okay, that is fine. I mean, now from a functional perspective, we agree this is what we need, but how do we do it? Okay, and we cannot go to the real system to develop all this infrastructure. We neither can to develop all this control infrastructure, or all this control system, hierarchical control system, based on separated assumptions and separated developments. Therefore, it's necessary to generate a kind of platform, and it was the Intelligent Clean Energy System Laboratory of the system, a Smart Energy System Laboratory, where what we have in the beginning are two simulators. Okay, these two simulators, one of them is focused on simulating, let's say, phasors with a sampling time of about 10 milliseconds, and the other one, it is the RMS simulation, and the other one is the EMT simulator, which is simulating time-based signals, okay, with a sampling time of around 50 microseconds, 100 microseconds. Both simulators are connecting each other through Dolphin, okay? So, well, with this, we are going to be able to emulate or simulate the grid and the power converters. And now we need to connect here the equipment that is connected in the grid, okay? For example, the RTUs from Schneider. In this case, our colleagues from Schneider, they adapted the RTUs that were physically installed in the grid to be able to transfer signals to our, let's say, grid simulator. The same from our colleagues from Esther, okay? They adapted their PMUs in order we were able to receive this, our grid simulator was able to send signals to these PMUs in order they were, let's say, collecting signals. And in reality, as well, from Schneider, we developed all the SCADAs that eventually were implemented in reality in advance. They were implemented here, and all the communications, external communication, VPNs, firewalls, other issues, all this demilitarized zone was already also implemented here, together with the high performance computing. All the optimizers and so on were implemented in other equipment. In addition, we didn't simulate controllers, but we used real hardware controllers, okay? I mean, the power converters, the controllers for the areas, and well, and we included other, let's say, other equipment that we have already in the lab. Therefore, at the end of the day, we constituted this setup, which in reality, this is a mock, and this is the reality. Sorry, you can see here the reality. I mean, this is the design, the first implementation that was deployed in Andalusia, in Spain first, okay, during the first stage of the project, and later it was transferred to Luxembourg, where eventually we were able to run all the, let's say, validation stages of the project, okay? For doing that, we had to transfer all the analysis of the grid from the offline simulation to the real-time simulation, okay? That required us to develop tools and scripts that were not provided by the simulator manufacturer, by Opal. That today, they have it as a product, but at the time we developed this project, that was not available, therefore we work on that. The systems, I mean, the simulations in time and the simulations in the phasor domain had to interact each other. We implemented this by using a Dolphin real-time communication bus. Therefore, in such a case, the power converters simulated at the right, okay, the switches with this 50 microseconds resolution were interacting with the grid, which is at the right. The phasors of the grid simulated at 10 milliseconds resolution. And something which is important is you can see here, and this Dolphin is the one connecting the two domains, the real-time domain and the phasor domain. And in the middle is where we had, let's say, all the controllers, okay, the second level controller, the area controller, the first level controller, the point of command coupling controller, and the power converter controller, okay? We're using all the hardware. Therefore, in the simulator at the left, we simulated the grid for Greece and from Cyprus. This grid was generating the same signals as we had in reality. The second level controller would be reacting to the control conditions in this grid. Based on that, would send references to the first level controller, and the first level controller would be also sending references to a control board of the power converter, which at the end of the day was controlling the switches of the power converter that was simulated in this second let's say, simulator. And both simulators mentioned are communicated each other by this Dolphin fiber optic link, and based on that we were able to close the loop. Okay, that was very relevant, and based on that we were able to develop the first version of the SCADA that eventually were also implemented in the final applications. There was not other way of doing that. Okay, therefore we developed first a SCADA in the lab, and later that was reproduced and scaled in the different application with all the parts of the SCADA. And this is a very important part that we did in this project. Okay, we developed what we call communication-based hardware in the loop. Okay, what I mean is the grid was modeled in a simulator, which is the one at the left, that could be, for example, in Sevilla, in Spain. And by using communication networks, we have the physical, or we have the second element, okay, the second computer, or maybe the real hardware located in a different facility, and we would send the commands and the feedback signals by using communication networks and using all the real infrastructure. Okay, this is a very relevant advance in this project. Okay, or of course there are other let's say projects where this was implemented, but in this was quite new, this kind of novelty. And well, we used this for example, in Luxembourg, we were simulating the power system in Greece, for example, sorry, in this case in Cyprus, and by using communications, we were sending signals both to the site, to the factory when the battery was in Spain, in Sevilla, or maybe even when the battery was already installed in Cyprus. Okay, so before the battery was responding to the real signals from the Cyprus system, in the beginning, during the commissioning stage, such a battery was, and controllers were responding to the signals that were generated by this virtual environment. Okay, in such a way, it was possible to test the response of the battery in front of many different conditions under control. Okay, the same happened with Greece, with the World Package 6 demonstrator. We were generating the signals in Luxembourg, and in Greece, we were able to send, let's say, signal for the buses and references in order to test the batteries that were installed in the substation of the wind power plant in Greece. That allow us to make, as you can see here, many different, let's say, tests that are not possible to be conducted in reality because operating conditions in a real system are not controllable, let's say, or are not manageable, okay? So, well, this was what we did in this project. And just for concluding, okay, what I can say is, well, it was a very exciting experience, okay, very challenging, because 4 years ago, implementing all this loop was a real challenge, okay. We had some experience on working with this kind of system, but well, we made a lot of work, let's say, starting from the scratch. Collaboration with our partners from Abengoa, from Schneider, from Esther was essential, okay, in order to be able to adapt their, let's say, measurement units, the wide area measurement unit, their SCADA, their controllers to our systems. Of course, as well, our collaboration with the ones integrating and developing hardware, with HEMA, with Abengoa, that was a great experience for all of us, okay. We learned a lot, sorry, from this project. And the most important, as Giovanna mentioned before, the matter was we learned this communication hardware in the loop system is very useful for really performing tests under control conditions using real hardware, is even located in remote locations, okay. So this is maybe the main important lesson, okay. We were able to use all this setup for generating the signals for testing the equipment in factory, okay. So we were able to design all the factory acceptance test. Later on, the batteries were transported or were shipped to the final location, to the site, and we ran as well the site acceptance test using the same operating conditions as in factory. That was that were very excellent operating conditions. Therefore, at the end of the day, when the batteries were commissioned after the site acceptance test, we had almost 90% confidence, okay, such a battery would be responding well under real operating conditions. And afterwards, when they were operating during the validation state and the real operating condition, we were able to monitor, and in case monitor the system, and in case there was any discrepancy or any variation, we were able to simulate the case in our simulator running in parallel. This was a kind of digital twin, and we were able to, let's say, to diagnose to make some diagnosis and even some prognosis, some cases about what was happening. Okay, so well, that's all from my side. Really, thank you very much for your attention, and well, I am open for any question, if any, of course.
Thank you very much, Professor Pedro. And it's very crucial that we have this kind of design and simulation lab, you know, to study the system extensively. Is there any burning question? If not, I